Hello everyone, my name is Yeong-Do Park from Dong University in South Korea. Today I'm going to talk about the shunt current assisted one-step resistant element welding REW of the vibration damping aluminum to ultra-high strength steels. My presentation will composed of introduction, motivation, objective, experiments, resultant discussion, and summary. Many of the mechanical fastening method has been developed and applied to join aluminum and steel dissimilar materials. In particular, when aluminum is the upper plate and steel is on the lower plate, the representative method is resistant element welding, and other methods such as friction element welding, FSSW, EASW are also applicable. And when steel is in upper plate, FDS or SPR can be applied. In this research investigation, we mostly focused on the resistant element welding side. Resistant element welding involves the mechanical fastening using an elements. At this case, the element is welded to the raw steel plate using the resistance welding process. Therefore, it combines the advantages of mechanical joining and thermal joining principles. It can be understood as a thermomechanical joining technology. It combines the advantage of mechanical joining, which is the form fit, and thermal joining, which is the metallurgical bond principles. The applicable to a wide range of dissimilar materials can be possible, such as aluminum steel joint, magnesium steel joint, carbon fiber reinforced plastic and steel joints, aluminum titanium, etc. In here, aluminum 16 1.5 millimeter thickness has been joined with the hot stamp steels using element with a resistant heating. The very large nugget diameter secures the bond strength between element and steels. At the same time, this element head is pressing down the aluminum plates, which is working as an interlocking mechanism for joint strengths. Resistant element welding is a two-step process. The first is sub-assembly manufacturing, where the element is punched and inserted into the aluminum plates, and the second is mainline manufacturing, where the element and lower steel plate are resistance welded. However, in these two steps, it is difficult for a robot to find exact location of the elements in mainline manufacturing, and the possibility of the weld defects increases. Therefore, one-step REW resistant element welding was proposed that omits the pre-assembly step and starts from the mainline manufacturing by punching or piercing the element into the upper aluminum and simultaneously performing resistant welding with the lower steel in one step. In case of this one-step resistant element welding, the preheating process of the aluminum sheet piercing using a special jig device and the main welding process are carried out continuously. The proposed one-step resistant element welding device consists of the variety of systems, including our existing resistance welding gun system, an element supply device, and the device that places the element onto the electrode. After piercing the element with pre-joule heating, the element and bottom steel sheet are resistant welded with the main joule heating. However, its use is kind of limited to date due to the application of complex jig system. In our laboratory, we also implemented a one-step resistant element welding process into a simple system. We applied the current profile of preheating step using current upslope, which are suggested in various literatures, and main welding constant current applied to secure a successful fastening. In particular, when the main welding current increased, the nugget size of the resistant welding area increased and joint strength also dramatically increased. With knowing all the information about the one-step resistance element welding, here is the motivation of this research. A sandwich-structured aluminum panel with a thermoplastic layer between two aluminum sheets to improve the noise, vibration, harshness properties. The assembly is assembled by joining an aluminum sandwich panel with a thermoplastic into a steel plate. At this time, our laboratory proposed a two-step resistant element welding processes. However, in case of a two-step resistant element welding, the quality problems such as a delamination of the sandwich panel occur during the pre-assembly process of punching the element into the upper aluminum plate. So we attempt to solve this problem by applying one-step resistant element welding. However, due to the high resistance of the thermoplastic present in between the sandwich panel, it was impossible to conduct current for the resistant welding. Various methods were investigated to solve the problem of non-current conduction in resistant welding. In the paper below, the following three approaches were presented. There are shunt current assisted resistance welding, induction heating assisted resistance welding, and ultrasonic assisted resistance welding. Among these three methods, after reviewing the method, the applied shunt current assisted resistance welding was quite appropriate approach. We finally proposed shunt current assisted resistant element welding. The following is the objective of this research. The first objective of this research is the feasibility study of the developed shunt current assisted resistant element welding process to weld between the vibration damping aluminum and steels. Second, the effect of resistant welding process parameters on the joint strength and metallurgical degradation at the interface of the weld joint. Third, optimize the minimum pitch distance or weld spacing between the resistant element welding joints and the magnitude of the compensation current to secure each critical nugget diameter. For the experimental approaches, vibration damping aluminum and schematic illustration of the tensile shear test specimen has been shown in here. The top sheet vibration damping aluminum is a total 1.8 millimeter thickness, and the thermoplastic resin has about 0.2 millimeter thickness. Sandwich type containing thermoplastic resin between two aluminum sheets has a non-conductive material mainly composed of polyethylene. The bottom sheet is the steels with the 1.5 gigapascal hot press formed with thickness of 1.2 millimeter, and element is the 20 mmP4 boron steels, and body height is 2.1 millimeter. To use the one-step resistant element welding process, welding is performed on the surface of the electrode, so the electrode can support the element. To form a path for the current conduction, shunting clip made of stainless steel has been implemented. During the preheating stage, one-step resistant element welding, the temperature of the entire welding area rises with a high pressing force. As a current bypassing the thermoplastic resin layer, the heat generated along the clip is bypassed through the steel plate, enabling the preheating. There is no need to apply the shunting clip for the subsequent welding for one-step resistant element welding point, and the previous weld point, which is the shunt weld itself, acts as a current bypass. A second or more welding point, shunted weld, can be formed without any further clip application. For the experimental procedure for optimization of the process parameters, preheating time for piercing, which implementation of the optimum pulse profile to secure element press fit possible to delete the existing pre-assembly processes. In the preheating stage, the upslope profile suppresses the surface heat generation and improves the contact characteristic by applying low current at the beginning of the welding. In main welding, inducing nugget formation at the interface between the element and lower steel plates. The following is the suggested welding process parameters. The next are the results and discussion of this research. This slide explains the effect of current and electric force on nugget size or welding quality of the one-step resistant element welding. With the pressing force of the 5 kilonewton or 6 kilonewton, when we increase the welding current, it gradually increases the nugget diameter between the element and steel sheet. When the welding current was increased from 8 kiloampere to 10 kiloampere at 5 kilonewton and 6 kilonewton pressing force, nugget diameter increased from 4.34 millimeter to 4.66 millimeter. All of this process has been accomplished by the shunting current clips, and also the upslope preheating has been applied, and then main welding was done with the resist heating between the element and bottom steel sheets. No special defects were observed in the weld area, and as the current increases, degradation of the upper aluminum near the interface was observed. Maybe some of the melting of aluminum has been occurred. At the same time, some formation of intermetallic compound can be expected, which will be explained later further. An excessive deformation of the element was also observed. This kind of excessive deformation of elements may cause a lot of pressing down of the element, and which finally lowered or degraded the joint strength of each weldments. This is the effect of squeeze time on nugget size. The squeeze time is the time before the main welding current or preheating current applies. So when squeeze time increases, pressure is applied for the long time, which facilitating the movement of the thermoplastic resin existing between two layers of the aluminum. The nugget tends to grow gradually. As the long cycle, such as 1000 milliseconds is applied, nugget grows significantly, but the element collapses, melts excessively. The cycle time increases. The shrinkage cavity also occurs inside. The squeeze time was determined to be less than 800 milliseconds. However, the mechanism of this squeeze time need to be on the weld quality need to be further investigated. For the resistant element welding joint, as a resistant welding current increases to the 10 kiloampere, the shear strengths are quite similar level with 8 kiloampere, which is a quite interesting results. The fracture mode are apparently different as interfacial fracture and base metal fracture. However, the joint strengths are similar level of 4 kilonewton. When applying welding current of 8 kiloampere, the increase in fracture load was not quite rapid. An element deformation seems to be the main reason of the load increase and result in interfacial failure between element and lower steel sheet. This is attributed to the small nugget diameter and the observation of the notch on the cross-section. Crack propagate and fracture occur at the interface between element and steels. When 10 kiloampere welding current was applied, crack occurred in the aluminum heat effect zone due to a large plastic deformation on the aluminum side. With a large nugget diameter of 4.66 millimeter, the weld nugget has been sustained. The external loading and aluminum side fracture occurred in aluminum base materials. As results suggest that When enough nugget diameter is secured, then failure will be controlled by the aluminum sheet thickness. By confirming the joint strength and fracture mode of this welded joint, we derive the optimal condition for securing high-quality welded joint and applying aluminum damping plates to the one-step resistant element welding processes. With the larger, higher grade thickness of the aluminum is applied, then this result may differ and the failure pickup load will be much higher than this condition. In case of joining between the aluminum and steel dissimilar materials in the automotive car body, welding is mostly done continuously near the first weld point in series. Therefore, the first spot weld point acts as a shunt weld and shunt clip for the shunt current assisting is no longer needed. Therefore, in case of the spot welds near the shunted weld, it acts as a shunt current spot welds for the further one-step resistant element welding. In order for a nearby spot weld to play the role of shunt current assisting, it is necessary to derive the minimum weld spacing distance. Additionally, a maximum weld space distance that does not require a compensation current value is also required. The difference between shunt weld nugget diameter and shunted weld nugget diameter become almost zero when weld spacing is above of the 60 millimeter, which is a minimum distance for no compensation current. However, the weld spacing is too large, more than 70 millimeter, the shunt current assisting is no more possible for one-step REW resistant element welding. As the element is pressed in, the heat generated is transferred to the aluminum material itself. At the same time, the thermoplastic resin is squeezed out from the interface between two sheets of the aluminum. As a result, a molten zone was formed in the aluminum vibration damping plate, showing the microstructure and solidification structures characteristics. It was formed that the aluminum melted area confirmed that the aluminum melted area showed a dendritic microstructure forming a coarse microstructures. As it moves away from the element, gradually it lowering the hardness through the here. We also analyzed the microstructure of each area where the elements and the raw steel plates were melted. The molten part of the element and steel shows the overall martensitic microstructure and very high hardness value of the 535 HV due to the high cooling rate of the resistant welding. Hot press forming steel and element heated back zone show the low hardness value of 273 HV due to the some of the ferrite formation and heated back zone of the element steel show also similar microstructures. Because the resistant element welding is a dissimilar material joint, the formation of the intermetallic compound, which deteriorates the property of the weld zone, actually occurs. Therefore, to analyze the intermetallic compound development, EDS line analysis was performed on the intermetallic compound part formed between element and aluminum. There has been about the 2.5 micrometer layer of the intermetallic compound has been developed. However, we found that it did not affect the quality of the fastening due to the development of the intermetallic compound layer in applied welding parameters. However, with excessive heat input, this may cause the degradation of the joint due to the very large intermetallic compound formation. Here are the summary of this research. Current bypass shunting clip application to the one-step resistant element welding process with the vibration damping aluminum materials was feasible process to secure the weld joint strengths. Combination of 6 kN of pressing force and 10 kA of welding current secured all the pull-up failure mode and quality standard, nugget diameter and tensile shear strength perspective. Since the nearby shunt weld spot itself acts as a current bypass. Continuous resistance element welding can be applied to shunted weld without applying any additional shunting clips. The weld joint pitch distance or weld spacing of 45 millimeter is the distance at the first shunt effect occurs at the compensation current is required. So the joint distance of 60 millimeter or higher more is required to secure the critical nugget diameter. Thank you for all your attention. Thank you very much.